plus 2x equals 0 has one real root and two complex roots. One real roots and two complex roots. Verify that 1 plus 2i is one of the complex roots. Okay, so we have to verify that. Okay, basically to verify if it's a factor or a root, okay, basically if you sub 1 plus 2i into the x, it should give you 0. Okay, that's what it means. Okay, if that's one of the root, meaning it's a factor. Okay, we have done factor theorem, it's the same thing. So if that is one of the root, then it should give us 0. So I'm going to sub 1 plus 2i into the equation and then find out whether it gives us a 0. Okay, it should. Okay, so let's do that. So before that, okay, it is going to be difficult if I sub 1 plus 2i cubed. So let's do that separately here. Okay, so 1 plus 2i, I'm going to multiply by 1 plus 2i. So when I expand this, I'll have 1 plus 4i plus 4i squared, right? Okay, 1 and then 2i. Yeah, okay, so let's expand or simplify, so which will give me 1 plus 4i minus 4, because I squared is negative 1, and this is negative 3 plus 4i. 1 plus 2i multiplied by 1 plus 2i is negative 3 plus 4i. Next, what if I have negative 3 plus 4i multiplied by 1 plus 2i, because this is for x cubed. Okay, so what do I get? Okay, let's expand this. So negative 3 and then minus 6i and then plus 4i, and then you have 8i squared plus 8i squared, and it's given that that's 10, no, so 10 minus 2. Okay, negative 2i and 8, that's negative 1, so negative 8, and you have negative 11 minus 2i. So this is for x cubed and this is for x squared. So now let's sub this inside. Okay, when I sub this inside, I have an equation. So separate color. Yeah. Okay, so you have 2x cubed plus x squared plus 25 equals 0. So 2 bracket x cubed, which is minus 11 minus 2i, plus x squared, which is negative 3 plus 4i, plus 25 equals 0. Okay, let's expand this. So negative 22 minus 4i minus 3 plus 4i plus 25. Yeah, so negative 22 minus 3 is negative 25 plus 25, that's 0. Negative 4i plus 4i equals 0. Okay, so verified. Okay, so this is how you do the first part. Okay, that's done. Now write down the other complex root of the equation. Write down the other complex root of the equation. So if 1 plus, this is part 2, if 1 plus I is a root, then the conjugate is also another root. Therefore, the conjugate is 1 minus 2i. Okay, so that's the other root. Okay, the next question. Let's sketch an Argon diagram showing the point representing the complex number 1 plus 2i, show on the same diagram the set of points representing the complex number z which satisfy modulo z less equals to z minus 1 minus 2i. Okay, so I've already jotted down the values over here. If we look at it, okay, the moment you have z, try to split that. Okay, so for those who are not sure, for those who know, okay, very good, you don't have to do anything. Okay, so if I split that, it's z minus 0 plus 0i, which gives you the coordinate 0 0, and then you have z minus 1 plus 2i, which gives you the coordinate 1 2. So basically what they're asking is sketch the Argon diagram, an Argon diagram showing the points representing the complex number 1 2, show on the same diagram the set of points. Okay, set of points meaning they're looking at a set of point. For this, it's basically a locus. Okay, a locus, and since 0 0 is equal to 1 2, so I'm looking at a locus that is exactly perpendicular between these two points. Okay, these 2 points, that's what I'm looking at. So let's draw, okay, to find out. Okay, so I have imaginary, so that's I, and then this is your real axis. Okay, and you have positive 1, positive 2, positive 3. It's not accurate, but it still works. That's I, that's 2i, and that's 3i. You don't have to go anything beyond that. So that's negative 1, that's negative 2, and this is negative I. Okay, and that's your origin. So we know z, modular z, okay, the coordinate is 0 0, so which is at the origin. Okay, and then the next point that we have is z minus z1, which is 1 plus 2i. Okay, I've already proved that. So from that we know it's 1 2, the coordinate is 1 2, so let's label 1 2. Okay, let's label 1 and 2. Okay, so 1 2, so that's the coordinate 1 2, and this is 0 0, so that's z, so I'll label this as z1. Okay, so z1. So now you have to draw, okay, the question says z, okay, equals to modulo z equal to z minus 1 minus 2i. Okay, so where is the locus that's equidistant? Okay, the distance is equal between them. Okay, and it has to be a, if this is the case, okay, if it's equidistant, then it has to be a perpendicular bisector. Okay, it is a perpendicular bisector. So if I draw a perpendicular bisector, that's not the one. Okay, before that I just want to make sure that I have a straight line. So perpendicular bisector, the point that it meets is at the midpoint between these two. Okay, midpoint. So if you look at it, that's 2. That distance is 2. Your vertical axis or your y-axis, imaginary, you have 2. So halfway 2, we come down to somewhere here. So definitely it's 1. Okay, your y value will be 1. And halfway between your real value, which is, that's 1. So halfway should be half. So this is where it meets. Okay, that's where it meets. So I'll use a separate color. So that's where it meets. So what is that point? So halfway in your real value between 0 to 1, halfway is 0 0.5, and halfway between 0 to 2, which is 1. Okay, so that's the coordinate. So if I draw a perpendicular bisector, that bisector should be a locus that passes through, it's a perpendicular bisector, passes through exactly in the middle, and it will certainly be a right angle, okay, point that intersects, okay, between, let's say, z, and I can label this maybe let's say m. Okay, midpoint, so m, so between z, m, and maybe that's n. Okay, z, m, n. Okay, so it should definitely be a right angle. So it is a straight line and right angle, okay, to the z and z1, okay, between the point z and z1. Okay, so if you can prove this, draw and show, then As long as you have all your points correctly labeled and with the perpendicular line, okay, which is the locus, then I don't see any reason why you wouldn't get the full mark. Okay, I hope this is uh, you know clear.